Welcome back, ladies and gentlemen. Want to look at this real quick. There's a couple terms that you're going to run into, and they're very fundamental to doing work in physics. Not just physics, but also other branches of science, but particularly physics. Qualitative versus quantitative. A qualitative understanding, well, is the word itself is going to give you a clue, right? This right here. It's like you have the quality of something. You have something you can say about it, the type or the direction, but not necessarily an amount. Because when you have a quantitative understanding, that's when quantity. That's when you have an amount, a number, a measurement, right? So let's write this down, because I'm going to be asking you for your qualitative response or understanding or description, and also your quantitative understanding or description. Qualitative. So you understand something about it, like you can say, well, it increased or decreased. Then you're saying something qualitative. It responded, and you know the quality of the response. You just don't have any amounts or quantities. That's where your quantitative comes in. So here for quantitative, you have data. You took actual measurements, or someone else did, providing you with numbers, with values that you can talk about. And this is important. Both levels of understanding are hugely beneficial. But we're going to focus in this video on quantitative, because when you have data, when you've taken measurements, you will almost always need to graph that data. And the reason why is that it can be much easier to see patterns and to make meaning of the data when you look at it visually instead of just staring at the numbers themselves. It can also allow you to make predictions, and in fact, this is a very important way that theories are tested and verified, or tested and found to not work, depending. So we're going to look at graphing, and therefore we're looking at quantitative specifically, at least in this video. Now, when you're getting to graphing, you have to understand something. Okay, in an experiment, you've got some variables, and they're called dependent or independent variables. Right, so now what's the difference between these two, dependent and independent variables? Well, in the experiment, you're in control of one thing, you're changing one thing, and then you're watching something else to see how it responds and what happens. So it's the independent variable that you change, that you control. And then it's the dependent variable, it turns out, that you are watching. This is the easiest way I've found to remember these two and the difference between them. So, in any experiment, you're going to change one thing about the situation, and you're going to watch something else to see how it responds, or you're going to watch to see if anything responds. Right? You may not know what it is right away, but you're watching, and you want to see what happens after you've made this one change. So there you have it. You have control over your independent variable, and you have some changes, hopefully, taking place in a dependent variable. And this matters because when you go to make your graph, you have your x and y axes, your x-axis and y-axis. And you say, well, which variable goes on which axis, right? Here's your y-axis, your x-axis typically. And the tradition is this, that your independent variable goes on the x-axis and your dependent variable goes on the y-axis. That's sort of the tradition. And you usually do want to do it that way. You want to follow that tradition, absolutely. So you also want to pay attention to data ranges. So we got that going on. What is the range of data? What is the range of the numbers you're dealing with? Because that's going to help you determine the scales on your graph. You have to look at the numbers, think about them for a second. You want labels on your graph with units. That matters. Oh, what else? You're going to plot points. So plot carefully. Okay, not plot. I can spell, I swear. Carefully, please. Oh my goodness. How often have I seen graphs literally drawn real quick, hastily, like this, and you go, oh, and I see, and okay, and there's my graph. Done. Ta-da! Yay! I passed physics. No. Don't do it like that. Please. Don't do things in haste. Don't be lazy. Plot carefully. Okay, you're also going to need a line of best fit. It will either be linear or curvy, and it's up to you to think about your data and figure out which is the best option for your graph. Is it a linear relationship? Then you draw a straight line of best fit. If the data shows a curvy relationship, then you have to eyeball that curve in there, and it's all golden. So we're going to look at this. I have some stuff for you. First, here's some data, right? Check it out. We have a spring length, or a spring length. We have a spring. We are going to use this little piece of paper, a little piece of scrap paper to give you a visual. We have a spring hanging, and on this spring we attach different masses, right? And for each mass that we attach, we measure the spring length. Cool. If we attach more mass, we see that the spring gets longer. Awesome. That's our data. Which is which? Where's the dependent and independent variable here? So which one were we changing and which one were we watching to see what happened? We changed the mass and we watched the length and to see how the length responded. So the mass is going to be our independent variable. The spring length will be our dependent variable. That tells us where on the graph to plot these things. All right, so how many data points do I have? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 data points. Cool. And I want to make sure I plot things carefully. And so how about data ranges? Because this is going to help me. The range here, I've got 0 to 35, and the range here, the biggest number is 16.4, so I'm going to go 0 to 16.4. Watch what happens, right? Here's my graph. Boom. Save you the time. I'm going to spare you the time of watching me actually create this graph. All right. So look, I've got my graph. I used a straight edge and everything. It's totally awesome. Except it's not. What are the problems here? There are issues, to be certain, right? Well, okay. Did I plot my points carefully? Did I eyeball this line of best fit? Because clearly it is a linear relationship. Did I eyeball that accurately? Well, yes, I did. What are some of the issues, though? Obvious issues. Good gravy. Okay. No units there on that label. No title at the top of the graph. Why is there no title? Because I don't even have room for a title. Look at this. Look at this monkey fight at the zoo kind of way I did this whole scale. This is ridiculous. Did I need numbers up above 16? Yes, I did. But I don't need them way up here in the margin. This is silly. Look at all this unused space on the scale. It's unnecessary. It looks terrible. Holy moly. All my data is squished up into that little tiny space on the graph. And it looks terrible. This is not a graph you want to turn in, right? Are there other issues? Well, the scale here for mass looks like it's plotted evenly, consistently. Well, that's fine. The scale here for the length of the spring, well, it looks like it's plotted consistently. But there's no need to start way down at 0. I don't have any data from 0 to 13 point something. I can leave all of that out. And when I do that, I leave everything below 13 out of the picture. Look how good this graph looks now. Still have consistent scales. It looks like 5 squares, and then I go to the next whole number, 5, 5. Yep, that's good. I've plotted carefully. I have my line of best fit carefully drawn. I have labels with units on both axes. I have a title for the whole graph. So this is a much better graph, much nicer construction of the graph. And now, so what's the first thing I do? Okay. You see a graph, and I'm going to write this here since I have space. You don't necessarily want to do this all the time on the graph. But if this is in your notebook or your journal, you've got room. That's cool. Linear. When you see linear, find the slope. What is the slope? Okay, I got to find the slope. Slope is rise over run. What does that mean? Common mistakes when I do the slope. I could take a couple data points and find, well, what's the rise there, what's the run there. But don't do that. 2 reasons why. Number 1, don't pick data points to find the slope. Instead, use points on this line that are not data points. And also, pick those 2 points to be far apart, please. So here's what I think I'll do. I'm going to find something convenient. For example, right about here, that guy, and I'll circle it so I can identify it easily. And way up here, oh, look at that. Look how it crosses right there. That's going to be an easy number to work with. So what's the coordinates of this point? I've got, it looks like 2 grams, and I've got 13 point, let's see, 2, 4, 6, 8, 9, about 13.9. Okay. Coordinates of that point, coordinates of this point. We're going to have, very easy, 32 and 16.2. Coordinates of that point. So my rise and my run are looking like this now. Okay, so I have here, my run is horizontal, that's a change in x values. My rise is vertical, that's a change in y values. What are those changes? So I'm going to do final minus initial. Okay, 6 on the, let's do the y values first. 16.2 minus 13.9, I get 2.3. That turns out to be my rise. The run, I have 32 minus 2, 30. So I can go back here and do my slope calculation. I've got a rise of 2.3. Dot, there's a decimal there, and a run of 30. I do that math. How many zeros are there in that? Let me find my answer. I've done this before, I swear. There's 1 0 after the decimal. Rounds to 0.077. And I do have to pay attention to one more thing here on the slope calculation. The y values are measured in centimeters. There are units there. The x values are measured in grams. There are units there. So my calculation of slope has units to it. Centimeters per gram. Okay. And then if I could or needed to, I could go further and talk about the meaning of the slope, but at least I have it. All right. That's important. So I have another data set for you. I want you to look at this guy. What if we just drop an object? What's it going to do? It's going to fall. So how far does it fall for certain times, right? If we measure the time, how far did it fall at those different time intervals? And so let's check this out, right? This is a thing we can graph. We have these data points. Here's what I've done. What's going on here? What's the issue? Well, look, everything is careful. Everything is nice and evenly spaced. It's 5 boxes all the way, 5 boxes all the way. Except, look at the numbers. Those numbers are these numbers. Uh-oh. You don't want to do that. So This is a huge issue. I have seen this. It doesn't come up too often, but I have seen this. Do not use your data points to create your scale. That's a no-no. That's always going to give you, when you do that, that's always going to give you this linear relationship, and you may get fooled by that, first of all. But second of all, look, I've got 5 squares there. That represents a distance of 4.9 meters. Then I've got 5 squares here that represents a distance of, well, 19.6 minus 4.9. So that's going to be, that's 14.6, 14.7. So this was 4.9 meters. This was 14.7 meters. That makes no sense at all. That's yucky. No bueno. So I want to highlight that potential issue for you guys. How would it look if you do this correctly? Well, maybe something like this. Here's my data. After 1 second, it had fallen 4.9 meters. After 2 seconds, it had fallen 19.6 meters, almost 20. That's why it looks like it's on the line. I did plot carefully, I swear. After 3 seconds, it looks like it has fallen 44 meters, almost 45. And so then after 4 seconds, and after 5 seconds, and so now check this out. All right. Is this linear? Well, if I do this with the graph paper, you can really see a curve in the data, right? Including the data point right here. Oop, you can't see that. Right there, sorry. At the origin. Look how obviously curvy that is. So, I need to eyeball this line of best fit, and it's not going to be a line technically, it will be a curve. Do I have to hit all the data points? No, but I want to best represent the data, all the data, with this curve. So just trying to show, and that's not too bad, I'm off a little on that one, but it's not bad. Look, totally non-linear. Can I find the slope of this thing since it's not a line? No, I cannot. But excuse me, that's how you would properly graph a set of data like this. Now I want to show you something interesting. If you only had the first 2 data points, right? So let me pretend here for a second. If you only had the first 2 data, let's go 3 data points. If you only had those guys right there, then that would mean, grab something here to hide the rest of the graph with. I only had that. Boom, boom, boom. I had 3 data points. Can I tell of 3 data points if that's linear or curvy? No, I can't. Not really. How about if I go to 4 data points? It starts to look more obvious, but I'm still not sure. Guys, I'm here to tell you, you really need at least 5 data points to truly tell if something is linear or curvy, and to try to tell what kind of curvy relationship it's going to be. What kinds of curves could there be? Just real quick to give you a rundown, there is the possibility of a few kinds that we may run into here in physics. So watch this. Got a list here real quick. You could see some sort of quadratic or things with exponents, like y equals x squared or x equals y squared, that kind of business. You could see inverse relationships. You could see sine or cosine. Pretty regularly. These things happen pretty regularly in physics. And when they come up, you want to recognize them, and I'll help you out. Okay, this video is going on long enough. That was just some graphing basics for you. I'll be able to help you with more details. If you have questions, let me know. Thanks for watching. I'll catch you next time.